Hello, I'm David Tower, and welcome to the Theories of Everything program. Viewers, you may have noticed over the past few weeks our Asteroid Watch segment at the end of the program, and wondered perhaps why we've included it. Well, the reason is very simple, because asteroids and their possible impact on our planet are now big news. Of course, recently we've had a couple of false starts. In around about 1998, for example, one particular asteroid was about to hit, or would have perhaps hit, Earth in 2028, but it was found to be about 1 million kilometres further away from our orbit than had previously been supposed in the initial calculations. The second scare, if you like, was just recently, a month or so back, when an asteroid was projected to hit the planet in about 11 years' time, 2015, and it would be a very big planet, a very big asteroid, as the other one was too, around about 2 kilometres across, which would probably wipe out most of the planet. But again, the odds for that impact were then readjusted, recalculated, and they were deemed to be around about 1 in a million. So again, people sort of breathed easy. However, some recent research has shown that that's probably a little premature, because it's now been discovered, the latest calculations have shown that there's probably around a 1 in 5 chance of a very large asteroid hitting planet Earth over the next 100 years. Now, when I say a large asteroid, one, for example, that is quite capable of knocking out a large city, such as Sydney or New York. The odds of larger ones, say perhaps over 10 kilometres or over 5 kilometres even, are much lower, in the order of 1 every 100,000 years. But one that can take out a complete city, at least, or a large swath of a country, is not to be disregarded easily. So the odds have shortened, actually, and the odds have shortened because there is more information coming in all the time about the numbers of asteroids, about their possible potential impact, their sizes, their composition. But there's still a vast amount more to find out. Now, the risk, this sort of risk, a 1 in 5 over the next 100 years, is pretty substantial. I mean, apart from our intuition, which tells us this is a reasonable sort of a risk when you consider that the potential of the planet is at stake, the potential of life on this planet is at stake, even if it is only, one large city, about 5 million people. Apart from that, risk is always calculated by a calculation of two things. One are the odds, which we've just seen, 1 in 5 over the next 100 years, and the other is the impact. The impact, again, is the possibility of losing the planet. Now, or a large part of it. Now, we've had a number of discussions on this program about life in the universe, and there's a fairly high consensus now that there is bound to be a lot of life in this universe. The universe is probably teeming with life, at least at the microbial level. In other words, there's probably lots of bacteria out there, lots of viruses, lots of very small life forms that have started on planets similar to ours and with similar suns, for example. And there's an awful lot of suns in our universe. However, there's no guarantee that that life on any of those other planets will have emerged to anywhere near the level of intelligence on planet Earth. Going on probabilities, which I've looked at in previous programs, there well could be. And some of the calculations seem to suggest that there may be, in fact, hundreds or even thousands of civilizations in our galaxy alone that you could classify as intelligent civilizations, and well beyond ours in some cases as well. But there's no certainty about that, which means that if a large asteroid hit the Earth, it's not only extremely bad luck for everyone on the planet, on this planet, but it could be very bad luck for the universe as a whole. It could wipe out the only major intelligent life forms in the universe. But regardless of that, it's time for action. And the action has been pretty pathetic up till now. Up till recently, for example, Congress allocated $4 million to NASA to start to track these asteroids, to keep track of their orbits. $4 million. That's about as much as it costs to keep the Pentagon in coffee and biscuits, I would imagine. And this is something that may, again, eliminate life, perhaps major life, throughout the universe. The only form. Now, so the risks are substantial to us, and again, if you look at the whole nature of life, it's been a struggle for life on any planet, and on this planet we've seen that struggle. We've seen the struggle go not only to the present form of Homo sapien, but our civilization. We've struggled to develop a civilization over the last 10,000 years. And to think that only that amount of money, the amount of money it costs perhaps to make a low-budget film, is being spent on tracking the major potential eliminator of life in the universe, it's just incomprehensible. Now, if we go back and look at the evidence for previous impacts, there's lots of it. For example, if we look at the moon, for example, the moon is absolutely pockmarked with craters. In fact, if you take any part of the moon 100 kilometres in diameter, there'll be at least 50 craters, most of which will be at least a kilometre wide and larger, in any 100 kilometre diameter patch. And that was confirmed by the moon mission in the 60s, because lunar rock actually was brought back. It was examined and dated from one of these areas. So the inferences have been able to be made fairly accurately. And if we look at planet Earth, especially with the new radar imaging techniques, surveys that are being done from spacecraft, etc., from satellites, it's obvious that there are some very, very big craters. There's a number. For example, there's one, the Yucatan Peninsula in Mexico is the one that's most cited. It's about 180 kilometres across. That was the one that was supposed to have wiped out the dinosaurs, probably. Now, that would have taken probably, the estimates are, about a 10-kilometre long piece of rock, an asteroid, and it would have hit at roughly 50 kilometres per second. And you can work out the energy from the simple formula, kinetic energy formula, a half of the mass of the object by its velocity squared. And it comes out to about 1 billion megatons of TNT. Now, a 10 megaton bomb is a pretty big one by any standards. But 1 billion megaton one is massive, and of course it had a massive effect on our planet. It caused, of course, a complete decimation of all plant and animal life, including the dinosaurs. Temperatures soared. When you get an impact like that, you get an enormous release of that kinetic energy in the form of heat. So temperatures would have gone to at least 1,000 degrees centigrade. Everything would have burnt. Huge winds would have started, at least estimates of 500 kilometres per hour. Vast amounts of soot have been discovered across the planet, dated around about that time, 65 million years ago. Around 70 billion tonnes of it, in fact, which was still only a small proportion of the amount of life burnt. Just about everything went up in smoke, and what didn't would have had a very severe nuclear winter following, and that would have lasted a long, long time, hundreds of thousands of years. And again, there would have been an amount of global warming that would have made our global warming look very small indeed, plus noxious gases, nitrous oxides and so forth. Now, there's a number of these craters, the one in Mexico, for example, but also one in South Africa and Arizona of about the same order. These are the very big ones. Of course, when you get a 10-kilometre lump of rock, the atmosphere, our atmosphere alone is about 10 kilometres. That's the breathable stuff that protects our planet. And so, of course, it would have just plunged straight through that. And, of course, the deepest oceans, and, of course, there would have been massive tidal waves as well, are around 2 or 3 kilometres deep. So, all in all, it would have been a pretty nasty time. And but if you want to get closer to the present and you want to see the devastation or understand the devastation that could have been caused by an asteroid hit of, say, 100 metres, then all you've got to do is look at Tunguska, which in the 1920s, it's a heavily forested area of Siberia, Russia, got hit by an asteroid. The asteroid didn't even get to the ground level. It just exploded above the forest, and it just knocked over completely thousands of square kilometres of forest. Massive fir trees as if they were just matchsticks, and that was only an asteroid about 100 metres long. Now there's been a lot of documentation and a lot of tracking of asteroids in recent years, despite the minor budgets that have been around. Because a lot of work has also been done outside the government. It's been done by universities and programs such as Space Watch, University of Arizona, and many amateur astronomers as well. Unfortunately, their telescopes aren't large enough to be able to sight anything but the very largest asteroids. The very large ones have been documented, and most of the let's say over 200 kilometres, very big ones. But from 10 kilometres to upwards to 100 kilometres, most of those have been documented, but not very many at all in the range, and there's probably a couple of thousand in that range, but in the range 1 kilometre to 10 kilometres, not very many at all. And of course around that 1 kilometre mark, which again is sufficient probably to knock out a large, not only a major city but a large part of the planet as well, there's probably 1 million of those sitting in the so-called asteroid belt between Mars and Jupiter. I'll come back to that in a moment. So you can see there's a lot of work to be done. There needs to be a whole array of telescopes, and there needs to be constantly monitoring, surveillance, 24 hours a day of asteroid orbits, which cross Earth orbits quite frequently, near Earth orbits, near Earth asteroids. So even though we had a couple of false alarms, that's unfortunately not a reason to be complacent at all. So viewers, where do asteroids and their cousins, comets, meteorites, etc. come from? Well, they're leftovers from the early formation of the solar system. They're the lumps of rock and, in the case of comets, ice and dust that didn't quite make it to become planets or even planetoids. They're relatively small, in other words. There are some large ones, but most of them are quite, again, relatively small, around that 2 kilometre size mark or smaller. As the aggregation occurred from little bits of dust combining, forming first of all 1 millimetre long and then gaining momentum around the Sun, so they didn't impact each other and break up. They kept aggregating as they were drawn to each other and they stuck to each other. And then once you reached an aggregation of around about 1 kilometre in length or size, gravity then kicks in. Gravity is a relatively weak force, but earlier the electrostatic forces probably played a role, but then gravity kicks in and draws more and more of these little planetesimals to it. So you get the aggregation into larger groupings and eventually planets and moons. Now, in between, again, the inner group of planets, the hard rocky ones like ours and Mars, and the outer group, beginning with Jupiter, you have the leftovers. You have the asteroids. As I said, 1 million of them, 1 million pretty big ones, around about at least that kilometre mark or close to it, at least in size. And then that's about so-called 2 to 3 astronomical units away from the Sun. An astronomical unit is about roughly the distance between the Earth and the Sun. So 2 to 3 times that distance is where they all hang out. And every now and again one of them gets kicked, goes through a gravitational perturbation from Jupiter. Jupiter's gravity grabs one, kicks it out, and it comes screaming out and crosses across the solar system. And it crosses, a number of them cross our Earth's orbit as well, and they're the ones we've got to watch out for. Now further out, around about 30 to 100 astronomical units, past Neptune in fact, past the major gaseous planets, is another belt called the Kuiper belt, after the Dutch astronomer. And that contains more of the icy comets. Comets have a core made of carbon, some metals, etc., but around them is ice. And every now and again they also get a kick from the gravitational fields of the giant planets, and they come in also. Remember, the impact of a comet or the impact of an asteroid, there's not much difference. It goes purely on weight, not on what they're composed of, ice or rock. So comets can be at least as dangerous as asteroids as well, and you don't see them coming because they just they get perturbed by not only the giant planets but by others, perhaps other stars as well. And there's another belt called the Oort cloud, after another astronomer, and it contains certainly trillions of objects, and every now and again other stars perturb the orbits of these, and one comes in on these long trajectories. So they can come in at any time. They don't just stay in their nice belts. The asteroid belt, the Kuiper belt, and the Oort cloud. And their trajectories are uncertain as well, viewers. This is the problem. This is what this team that just recently provided its results, this 1 in 5 in 100 years odds, came to the conclusion about. Tracking the orbits of these objects is not so easy because their orbits are fairly uncertain. They can change and shift as well as coming out of the blue. So that's the reason for those false alarms, by the way, because they were very hard to, the orbits are very hard to measure. First, they're very small objects, and secondly, they're uncertain in their orbits. Their orbits can vary. They're not like giant planets, which you can predict, which you can predict with some certainty. Viewers, it's one thing to keep track of these asteroids, the ones that cross over the Earth's path. That's not a terribly difficult task. What is difficult, of course, is taking preventative action if any of them get too close. And of course, this is what this funding urgency is about. At any time, as I mentioned, a rogue asteroid or comet could come into the circuit and could come perilously close to Earth, and will do eventually at some point in time. In the near future, in the next 100 years. It could be tomorrow, or again it could be in 20 years, it could be in 100 years. The point is we have to be ready for it, and to do that you have to understand the composition of the asteroids to be able to know what sort of action to take. So that's what a number of spacecraft, flyby spacecraft have been used for over the past few years, and again will be continuously in the future. There's actually 4 of them. The earliest one, of course, was the one that did a flyby on Halley's Comet, the Giotto spacecraft, and it flew around about 500 kilometres away from Halley's Comet, being blasted by grains of dust and ice and so forth in the process, but managed to take some very good photographs, showing that for the first time that comets, asteroids, etc. were really made up of rubble. They aren't sort of big chunks of very close composite rock or ice. Because of the way they aggregate, they come into these sort of groupings of rubble, and often in fact are split into various parts, staying together in their orbit. Binaries are very common. 1 in 5 comets and asteroids are binary, or split into 2 parts. There are all sorts of irregular shapes. They're usually dark. So, but in the future there'll be a number of, or 4 new spacecraft taking photographs and trying to understand the composition of these objects. One is and perhaps the Rolls-Royce of all of them is called Rosetta. That's put out by the European Space Agency, launched by them, and that will actually land instruments on a comet. It'll do the analysis right there. Rather than bring the bits of the comet back to Earth, it'll land even an atomic force microscope, mass spectrometer, gas analyzer, photographic equipment, etc. All will be landed, do their job, do the analysis, and send the information back directly. So that's the Rosetta spacecraft. And all these are due to deliver information or major information from about, from now till right through till 2005, 2006 and beyond. So that'll be extremely valuable. Now, already, of course, plans are being drawn up, and as I said, much more urgently, to try and work out how to nudge these massive chunks of rock and ice away from us if they get too close. The popular sort of way, and the one that has been featured in a number of movies, is to nuke these bits of rock, to fire a 1 megaton or a 10 megaton, which is about our limit, nuclear device at them, and hope to sort of either smash them to pieces or push them a long way away. Unfortunately, that scenario is completely oversimplified. First of all, because these meteorites are rubble, chunks of rubble basically, the direct impact of a nuclear device will have far less effect in moving it away as an alternative to if it was a big chunk of hard rock. And secondly, if it'll break it up, and if it does break it up into pieces, those major pieces may do far more damage than one big piece, in fact, if they land on Earth. So it's very problematic. If you want to really do a good job with a nuclear device, you explode it about 200 metres above, say, a 1 or 2K object. And it vaporises part of the surface, but pushes it, provides the momentum to push it out of orbit. Hopefully without smashing it into pieces, but the original calculations that it would move the orbit 10 centimetres a second away from its original path, which is tons if you've got a year or two to do this in, a year or two before the collision would occur, because by that time 10 centimetres a second can have a rather major effect and move it completely away into a different orbit. But unfortunately, again, because of the apparent nature of meteorites, this isn't going to work either, and probably only move it because 1,000th of that distance, because of the rubble type composition will absorb the energy of the nuclear blast rather than just provide momentum. So other alternatives are being proposed, including a softly approach. One is to put a little engine, a rocket engine propelled by nuclear energy, or some sort of solar radiation power that will provide an ion propellant, ions, a propellant that will stream continuously over a period of years, and like a rocket motor again, and move it into a different orbit. So that's one solution, except that these asteroids rotate as well as move along a particular orbit. So the motor has to be particularly well positioned to stop that rotation process basically so that the orbit can be changed accurately. And this is extremely tricky stuff. Another alternative is to position a large parabolic mirror, which will also over time make a difference to the surface. It will basically ionise the surface and add and provide a momentum, a kick if you like, as the surface streams away due to the heat from the mirror. Giant mirror, in fact, the size of a football field it'll have to be. It will gradually push the rock in the opposite direction. That's fine if you can position again accurately that giant mirror. And as another alternative is to cloak that meteorite one way or another with translucent little beads or some sort of white powder, whatever, so that it stops the solar radiation being absorbed into its dark interior, because comets are very good absorbers. Again, on their surface they're usually very dark, and they'll absorb radiation and re-emit it later on. This is called the Yarosky effect, as thermal radiation, which will have again the effect of providing enough momentum in the opposite direction to move the object. But again, you need lots and lots of time on your side. You need tens of years to be able to make an impact on that orbit that way. But anyway, one way or another, these techniques are being perfected in the meantime as the new spacecraft go out to find more information, to provide better information, so that a good strategy can be developed. But perhaps the best strategy, if you want to provide a cloak around it so the Yarosky effect doesn't kick in, perhaps we can employ Christo to wrap it in some nice shiny material. So viewers, there we have it, the most serious threat to humanity, and we're largely unprepared and certainly underfunded. There are other major threats to our planet as well. The nuclear threat, but you can negotiate a nuclear disarmament treaty. Global warming is a long-term threat, but you can also negotiate protocols such as Kyoto to reduce carbon dioxide emissions. But you can't negotiate with an asteroid. You only get one shot. When it arrives, we've got to be prepared. So Asteroid Watch will keep you updated on progress in this area. Regular updates that will provide an overview of the strategies and the evolution of knowledge in this area. It's an area that will be of major concern to us all. I'm David Tao, and you've been watching the Theories of Everything program. I'll look forward to seeing you again next week.